Thank you, Spencer, for your introduction. And also, I want to thank Professor Christian Geske for helping make this talk possible. And I'm very happy to be here today. First of all, I designed 2 title pages for this talk. This is the first page. Hope this works. Okay, great. That's the second page. You can see there's a QR code here. And so this is the same picture from your the flyer I just distributed. If you scan this QR code, you can access my notes for this talk, which is a paper. And on the back side, as you can see, is a poem that I wrote, very suitable for this talk. Just to prove that I wrote this poem myself, that's my handwritten notes.
Oh,
And I like writing poems, and those are the 2 poems I wrote for my discussions for Calc 3 and linear algebra when I was working for Professor Emerson and Professor Geske, and I invited them to provide a voiceover, and I made 2 videos out of the voiceover, and it's pretty interesting. So these poems are math poems. So if you take a look at the language, it's math definitions and math theorems. So it's a good way to help our students to understand the math concepts learned in this course. And what's interesting is Professor Emerson also clipped this the poem I wrote under his nameplate in front of his office. So pretty interesting. So I appreciate that. And so let's dive right in. Mathematics is a mountain. And for years, students have been given postcards from the summit. We're shown equations like that, E equals mc squared. Anyway, it comes from physics, but it's a math equation, right? Also very suitable. As if seeing them is the same as reaching them. But we are not at the top. We're trying to climb. And what a climber needs is not merely scenery. A climber needs a trail. So today, just like a good novel, this talk is divided into 2 parts, or in other words, it has 2 threads, the covert thread and the overt thread. That is the surface thread and the underlying thread. And for the surface thread, we have, it's pedagogical. So I designed 8 teaching principles. Hopefully, they're just my principles. Feel free to disagree or feel free to give me any comments. And the underlying thread is my math teaching atlas, which is what the paper, the notes cover. So we have 3 acts. So that's it. Next, let me start with a question. Why does math so often feel hard? Why does mathematics so often feel hard? Well, I've thought a lot about this question. So let me give you a claim. My claim is that it's not because the mountain is too high, but partly because the mountain is pretty high, but not merely because of that, but because the trails are often hidden. And by the end of the talk, I hope you'll agree that I've proven this claim. That's what this talk is about. And so as you can see, like this picture, the trails are usually this picture is designed by AI, not by you. Next. Let's start from the first principle, called principle of clarity. Make clarity the floor, not the ceiling. What does that mean? Well, let's start from this act 1, which is the solution to the problem. The answer to the question, like how to make math super easy to understand, or the way to do that. What I call what are clear trails? Let me form this. Let me start with this proof statement. This statement is very typical. It can be found in a lot of math textbooks, something like that. Let's prove statement S. Since A, we have B. From this follows that C. Therefore, D must hold. Thus, we conclude E, right? Very typical. And well, this and also what's worse, E often is not the same as the original statement S. So if you're a mathematician, I believe you've seen that a lot. And this proof usually works very well if you already know the proof very well. I claim I have like another way to write this. which is basically what this talk is about. I call it a routeway. So take a look from A to B. We have, since A, we have B. This is just a fact. A sentence doesn't mean anything. If I say A, right arrow B, and then I put a statement, a general justification P1 on top of it, where P1 says, given A, we have B. Now it's not just a sentence anymore. It has a soul, it has a trail. It can tell you exactly how A leads to B. Does that make sense? So that's one essential claim of this talk. Given A, we have B. So this, that is the inference unit. From A, we have B. This is not new. This formula or format dates back to Aristotle. And this is a picture of Aristotle in the 4th century, I believe. For example, let me give you a concrete example. For example, biologically, it's true, it sounds funny. Humans are apes, right? Apes are a super family. Humans, Homo sapiens, it's a species. Humans are apes. And Aristotle is a human. Therefore, Aristotle is an ape. That is how it works. Does that make sense? It's called syllogism, right? It's a totally biologically and mathematically valid proof. But what I want to do here is to generalize this notion and to sort of formalize everything from the inference unit. So let's start with the first definition called waypoint. I have a lot of things displayed on the screen, and I'll just highlight what's important. They all can be found in the paper in my notes. A route unit, by definition, is a unit of this form from A to B, where P is what I call the trail that explicitly justifies the transition from A to B. So that's how it works. And I call A and B waypoints. A is the initial waypoint, and B is called the terminal waypoint. Just give some terminology. This works. We have this form A to B. Next. A two-way route unit is just a special case of it. A route unit of this form, A to right, left arrow, B, where P justifies both directions. And when P is omitted, I call this route unit defective. Therefore, if you take a look at the textbook example I showed you, most route units are defective by my definition. Let me give you an example. Consider this trail multiplying both sides of an inequality by a positive number C preserves the inequality like this. If we have A less than B, we want to use this property multiplying both sides by 2. We have 2A less than 2B. This works. This makes sense, right? This is an example of a route unit. From the initial waypoint, we have the terminal waypoint by the trail P. It's not just to merely state the fact. It's actually a route unit because we have the trail P. It's not defective anymore. So that's the spirit of this definition. Sometimes we wonder, well, what if, like in the previous example, let's go back for a little while. The previous example, for any elementary school children, it works well, right? As long as they have learned this general fact, which P states, multiplying both sides preserves the inequality. However, for a kindergarten kid, they might not know this property P. They might not know P, why P works or the existence of P. So we cannot directly use that. In that case, for kindergartners or for those who haven't learned this property, this doesn't work well, although it's not defective. So motivated by this, let's introduce the next notion called base field and also B, irreducibility. Let's introduce this base field first. It just means the set of trails, for example, definitions, theorems, everything that we can use to justify an inference unit treated as atomic And we introduced the B irreducibility. What does that mean? Well, if P, the trail, is included in the base field B, we call this root unit B irreducible. So that's the definition. Let me give you an example. Go back to the previous example. Also, this is just formal justification. You can find them in the notes. I even used the instantiation lemma to justify that, but it's not essential. And the spirit is this. In the field of the elementary school base field, if we treat that, the elementary base field as our base field P, then this P is included in the elementary base field. Therefore, this root unit is irreducible by the previous definition. And that's what it means. Likewise, let me also point out in a more advanced base field, we can further simplify this root unit. That is, we can directly use ×2 because like in our teaching, for example, if we were a calculus TA, we don't want to reduce everything to the very basic format to this one, right? We don't have the time to do that in discussion or in lecture. So we can just directly use ×2 because like the base field can be increased or it can be broadened. So it includes not just P, this property, but also this special case. And this brings us to the next property, what I called a lemma, multiplicity, monotonicity under base field extension. This is very easy to understand. If P is included in a smaller base field, B here, and D is a subset of B prime, therefore, P, the trail, automatically is included in the larger base field P prime, right? Therefore, we have this conclusion. Every B irreducible root way is also B prime irreducible. For example, the previous instance, if the property P multiplicity like preserves inequality, this is included in the elementary base field. Therefore, this is included in the more advanced base field, like in calculus base field. So it is irreducible in both base fields. So that's what it means. Next, it's natural to extend our scope to consider the sequence of root units. That is more what we usually encounter. So I call the sequence of root units a rootway, or simply a root. It's like a long exact sequence. I don't know what exact means here. It's a long sequence. And so this is a combination of several root units. I call this A naught, the first one, the starting point, the last one, the destination, meaning the terminal waypoint of the last root unit. So that's it. And likewise, if a rootway is B irreducible, I mean, if each of its root units is B irreducible, we call the entire rootway B irreducible. Very natural definition. It happens a lot in math. Like if Markov chain, if every state is aperiodic, we call the entire chain aperiodic. It's like that. Next, let's give you a simple algebra example. If we have this sentence, well, this sentence is a very typical, again, example in many group theory textbooks. We might just state, well, since the order of the group G is P squared, it is solvable. If you don't know much about group theory, this doesn't make much sense, right? So we can further, first of all, this essentially corresponds to this rootway, actually a root unit. I call it a single root unit rootway. They're the same here when the number of root units is just one. If the order of the group is P squared, it is G, it is solvable. That's what the sentence essentially means. It is defective because it's bald, right? There's nothing above the arrow. So by definition, this is a defective root unit. It lacks the explicit trail. Well, when we actually teach our students, we might say something like this to make it more explicit. We know the order of G is P squared. Since every abelian group is solvable, it follows that G is solvable. However, this corresponds to, essentially, it corresponds to this root unit. From G order being P squared to G being solvable by the fact that every abelian group is solvable. I don't think it's easy to follow if you don't know group theory. Agree? You know, what does that mean? I don't understand that. So we show you what a really irreducible routeways would look like. It would look like this. From the fact that the order is p squared by the first trail justification, we have that, etc. For example, from the fact that G is abelian, we have G is solvable by the fact that every abelian group is solvable. This is much easier to follow. Even if you don't know anything about group theory, this makes sense because every step is irreducible. In particular, this routeway is irreducible. I hope it starts to make a little more sense here. Of course, you know, you might think, hey, Ivan is just, you know, trying to use the like graphical way to replace words. This is actually not what I mean. You can still use words. Words are perfect generators of lectures, right? What I want to emphasize is it would be much better. I mean, wouldn't that be great if we could make most routeways irreducible, not only non-effective, but irreducible. We can still use words to describe everything, but tell us the trail, tell the students the trail. I think based on my experience of being a student, I've 20 some years experience of being a student, it always works very well. For example, again, even if you don't know anything about group theory, this makes sense. Trust me, this does make sense. If G is abelian and every abelian group is solvable, then G is solvable. You don't have to know what abelian means. You don't have to know what solvable means. You can follow this logic. Do you agree? I can certainly follow this logic, even if I don't know anything about group theory. I think my 6-year-old nephew can also follow that because you know, because it's irreducible. So that's I used to create formula sheets for my students, and what I just described is like the theoretical foundation of creating such formula sheets. I asked my students a question in a survey. I designed a survey a few weeks ago for a course I'm TAing this semester, and this is my students' response. You know, I asked, "Does my teaching and discussion fulfill my commitment to clarity?" 100% of them said, "Yes, it does. It is mostly clear and easy to understand." I know it's a little showy, but I'm really proud to show you that because, you know, it means the framework works. The sample space is not necessarily too large, but at least, I mean, I have larger sample space. I have more evidence. I can show you more evidence, but it would be more showy. So like I'm very proud that of myself, of the framework, and also of my students for placing the trust in me, you know, for telling me that clarity can be achieved by this framework. And so this, well, clarity is, in my opinion, not, as I said in the beginning, not the ceiling, but the floor. In other words, I think as a TA, at least in my case, I'll always try to make teaching very easy to understand. Like I treat that not as a goal that I fight for, try very hard to fight the fight for so much as the ground I stand on. Like because our students trust us, and you know, our students sit in the classroom and listen to our discussion or lectures, and they want to understand what we're talking about, right? Like they are human beings with feelings, and if we make the courses not clear, then probably they'll not be happy. They'll be sad. They'll be sad that they can't understand anything. Their future is not bright anymore. So yeah, that's what I try to do by this framework to make clarity. Again, next, let's move on to the second principle of humility. Just like the spirit I showed in the survey, I'm not saying that you know, I'm great. I created this framework. I'm a great TA. I'm the best TA. Well, what I must say is we always should listen to our students, learn from our students, because good teaching listens. You know, we learn from them. This just like the feedback form in the previous slide shows. And, I have basically two goals in my teaching. Like at the beginning of when I just started my teaching career, when I became a TA, I wanted to become a really great TA because that means I can give my students a great learning experience. That's what I wanted to do. However, later, somewhere along the way, I started to realize this goal is about myself, so something doesn't really work. Of course, it's a very good goal. I want to be a great TA because I can give my students a great learning experience being the best TA. But later I realized what I really want to do is to give my students the best learning experience. That's my real goal one. To do that well, to achieve goal one, I can be a better TA, improve myself, because I can better achieve goal one, which is to give my students a great learning experience. And that's why humility is very important. We should always listen to our students because education is not about ourselves, it's about our students. That's what I always believe in. And because education for me is not a performance, but a promise of clarity, promise to understanding. And that brings us to the next. Also, I have this quote from an essay I wrote: how we react to criticism reveals a lot, speaks volumes about ourselves. We truly put our students first, then we should listen carefully, greatly, and gratefully to feedback from them. And the next principle is called should be the next page. It's called the principle of belonging, because that reminds us that the class discussion ultimately belongs to our students. I used to give, because I claim education is not the same as teaching. I think in my opinion, education, teaching is like the boundary, and education includes the interior, like the closure. And think of going to a movie theater when, like in the past, when there was no computer, there was no internet, we would go to the movie theater, but now we can stream from home, right? We can watch a movie from our home. Why would we still want to go to a movie theater? It's because we like to experience something there. We want to be part of the theater, It makes us feel warm, just like we would still go to a concert, a live concert, to see the celebrity instead of just listening to music from home using our AirPods. We want to go see Arnold Schwarzenegger standing there. I don't think Arnold sings. For example, Elvis, right? We want to, or Elton John. We want to really see them. We go there for a connection, a moment. That's why I hope our students come to our discussion, come to our lecture. The experience is what's worthwhile. And this semester I tried to play some games for them, not like grand games, of course. It's got to be related to what the course is about, like the name game, just for them to remember each other's names better, to serve the purpose of our discussion, to let them remember each other's names. For example, I would let them think of an adjective that shares the same first letter as their name, as their first name. For example, if my name is Ivan, I can just use the adjective iconic, right? Iconic Ivan. If somebody's name is Tom, they can say tumultuous Tom, or pedestrian Peter, or powerful Peter, right? I think it's a good way to engage our students. Or the fist bus game, like if it's multiple, like to let them count off around the room. If their number is a multiple of 3, they can say fizz instead of the number. Multiple of 5, say buzz. Multiple of 3 times 5 making 15, they can say fizz buzz. I usually start with 0 because 0 is a fizz buzz, right? It's a multiple of both 3 and 5. Actually, 0 is a multiple of every non-zero number. Also, a good game is You're the Expert. That is to let them, not really a game, just to let them walk us through the problem, let them be the teacher. And I will sit in the audience and let them enjoy the process of teaching. I think it's also a good way to help them review the course material. So very good. You can try that. Well, like if you like, or use other ways to engage our students. Next, 1.3 is refinement. I'll just glide over that. It's just the purpose is to formalize the process of making irreducible routeways out of descriptive words. So everything is very formal. Like refinement, I can prove refinement is a pre-order, etc. So just skip that. Next principle, I call principle of efficiency. That is to begin from what students already know. We've finished Act 1. Now let's move on to Act 2, familiar anchors connecting to known concepts. After Act 1, we've essentially become teachers that can make the course concepts and like the course content very easy to understand. However, we should aim further. We should, let's expand our scope, because in Act 1, we talked about individual routeways and route units. Now, why don't we do a common tricky math? Why don't we expand our scope from individual routeways to the collection, the set of routeways? Does that make sense? Just like in math, we can consider the functions, right, as a rule, or we can consider the set of functions. That is an expansion of our scope. Like we can consider the operators from functions to functions, or functionals, right, from functions to numbers. Next, so that prompts us to define the collection of routeways, which I call a roadmap like this. So for example, in this picture, we have two routeways. The first one is from A to S. The second is from also from A to S, but a shorter one, this green color. Let me point out, this green color actually has a pretty fancy name. Does anyone in the audience know the name of this color? Teal. This particular, corresponding to this particular color code, it has a fancier name.
Seafoam green.
Close. Very good. This color is also always called Mermaid's Kiss. That's the official name of this color, not a funny name. Those are all official names. This color is pretty funny. I like this name. It's called bittersweet shimmer. Think of it. If we tell our students, well, this bittersweet shimmer equation gives us that. So like our discussion more. Also, Purple Mountain Majesty. Pretty interesting names. Next, now our focus has shifted from simply ensuring each routeway is clear to determining the optimal routeway, the shortest, to utilize during instruction. Let me give you an example. Gato is a Spanish word meaning cat. So if a student asks us, well, what does gato mean? We can just say, well, it means cat. That's enough. We don't need to give them a zoology lecture, because cat is a familiar anchor. We don't want to tell them, well, what does gato mean? It's a small domesticated feline known for its agility and independence. It can typically climb trees and move swiftly along narrow structures. It's not familiar, right? Cat is a familiar anchor. Does that make sense? So, there's really no need to hear the whole climbing trees part. We know it can climb trees once we know it is cat, right? So that's the spirit of familiar anchors. I'm giving another example. Suppose we are teaching a child how to get to school. The child already knows two pieces of information, like the premise. First, they know how to travel from home to their father's office. Second, they know how to proceed from their father's office to the campus gate. Well, now, suppose we teach our students this way, teach the child this way. This is the most confusing way. Just like when asked what gato means, we say it's a feline, blah, 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 right? Here, it's akin to saying walk 10 feet, turn left, go 2 miles, turn right, take another left turn, maybe after the fifth, depending on the traffic. Well, maybe if this doesn't work, there's another way, it's a bit longer, or it's better to take a cab if you've taken one before. Well, let me teach you how to do that. Compare this to the one using familiar anchors. First, go to your dad's office, and I'm using father's office because father, we're talking to a child. Father sounds very funny. Like, Father, I stand ready to serve until thy wish is fulfilled. We don't talk like that, right? So go to your dad's office. From there, go to the campus gate, just like before. walk straight until the end of the road, turn right, and then you'll see the school. What's magical about this explanation is that it uses the familiar anchors, in this case, F and G. This corresponds to the shorter route way. It's more efficient. F actually means father's office, right? The letters even match. Pretty funny. G means campus gate. S means school. So this is a shorter, more efficient way. If you get the spirit of what I'm talking about, even if you don't follow the detail because time moves very fast, like a free group action. I usually like to use this analogy because we have trivial stabilizer. Every step takes you to a new orbit, meaning time moves very fast. Next, also, I don't plan to go to the detail about this example. I just wanted to show you, this is in my notes. If you know LaTeX, it's not easy to type that. So I just wanted to show you what I have in the notes. This example is also pretty good. This is from probability, random walks. Next, we have the next principle called principle of intuition. That is to show students why it is a natural step to take. Well, what does that mean? This brings us to the last act, Act 3, mathematical compass and driving simulation. With the insights gained from the previous sections or previous 2 acts, we have become educators ideally capable of making math highly accessible. This is all, already a very high goal. Like if you can do that, if we can do that, we're great educators. That's already amazing. However, we should aim further. Let's also explain the motivation behind each step. That is what I call the mathematical compass. A compass is just the underlying motivation. For example, in the dad's office example, a curious, inquisitive kid might ask, well, why you want me to go to my dad's office? Why do you want me to do that? What's the reason? What's the philosophy behind this? Why do you want me to go to my dad's office? This is why. This is not how. I, as the child, know how to go to my dad's office, right? It's a familiar anchor. I'm asking why. Usually that's a good sign, based on my experience, it's a good sign in our teaching if our students start to ask why this is true instead of how. Because usually when students ask why, that means they've already, most of the times, like in most cases, they've understood how the step is true, like how we can get B from A. They start, after knowing how, they've started to think about why we chose this step, what's the motivation behind it. And so that's what we can just answer this way, because your dad's office is a familiar place to you, just like your home. And you know how to get many places from there, starting from a familiar place. It makes things easier. That's called motivation, a compass. That brings us to the next principle, because we answered a question. I think it's important to notice that students don't want to be judged by their questions. We might ask, we want to, I certainly want a judgmental-free environment where we can ask any questions without being judged, right? And that's the best way to learn. For example, Newton asked himself a very silly question in the year 1666. Why would an apple fall down instead of falling upward or sideways, right? This sounds silly, but that seemingly silly question led him to the discovery of universal gravitation. That's the value of asking silly questions. Students are not on trial. The classroom is not a court. They don't have to call me your honor. We're not judging them. So I think it's important to notice every question has value. Next, driving simulation. What does that mean? It just means concrete examples. So we can ignore this definition, this more formal definition. If you know math, if you're more familiar with like parameters, you understand what I mean. But it just means, if you don't, it just means concrete examples. That's what it is. For example, 2 + 1, it can mean 2 apples plus 1 apple. It can mean 2 dogs plus 1 rose, right? Whatever. And speaking of that, concrete examples are actually pretty magical. For example, I asked my 6-year-old nephew, well, how do you understand 2 + 1? For example, 2, if I have 2 apples and you have 1 apple, together we have 3 apples. That's the best way to, a very good way to understand that. And I later asked him, well, 2 apples plus 1 apple gives you 3 apples. So how about 2/5 plus 1/5? He answered 3/5. It's pretty magical, right? A kindergartner can do fraction computations. And later asked, well, how about 2x plus 1x? He said 3x. He can also do polynomial algebra. So that's the magic of using concrete examples. Again, 2 plus 1, it doesn't only mean the most abstract definition, can be something concrete, like 2 apples plus 1 apple. Like this, I use this to mean abstraction without the support of concreteness is just like a tree crown floating in the sky, suspended in emptiness. It cannot grow. But if I think abstraction is always supported in concreteness, that is the soul of abstraction. Abstraction with the support of concreteness resembles this entire tree with vitality, right? With the tree trunk and the roots. It can even grow higher. That highlights the importance of telling our students the concreteness, like why we do this abstraction, why we generalize it this way. Like, for example, like this, g dot x, this means orbit, right? Sometimes denoted as O sub x. If we directly start with the most abstract definition from category theory, orbit is the image of the morphism, it's hard to understand. Not only is it hard to understand, it's hard to memorize if we do that. And it doesn't explain why it's called orbit, right? It doesn't offer enough intuition. Also, I'm not saying that concrete, abstraction is not good. I love abstraction. Abstraction is the base, the root of category theory to generalize everything and form them into a family, bring them together. That's a good thing. What I want to emphasize is that abstraction should always be supported by concreteness. I think that's a very important notion in math education. If we can tell our students why this is true, the motivation, and also how the concreteness supports this abstraction. Like this is the most intuitive definition, like a module. We know a module is, we can define it using their formal definitions like bilinear maps, associativity. But we can also say a module is just a vector, like a vector space over a ring instead of a field, right? That's another way of teaching that actually uses familiar anchors. That's another example of familiar anchors. And yeah, but this is a more suitable example. When we teach elementary school kids, or maybe not elementary school, like high school kids, the definition of even functions, we can use this. We can start with the most abstract definition that applies to all functions, like any function that satisfies this property, f negative x equals f of x. It's called an even function. I think a better or a more powerful way is to start with a concrete example. For example, like this, we start with f of x equals x squared. And then we plug in a special value like 3. We have f of 3 equals 9. And then f of negative 3 is always also equal to 9. So we have f of 3 equals f of negative 3. And we can generalize this to all functions. We call all functions having this property even functions. I think that's a better way to leave a more lasting mark on our students also. And also that explains why this is called an even function. Usually people don't think too much about that, but here's the answer. The name of even function comes from the power functions, because just like a topological extension, right? The open sets we call all sets satisfying the 3 basic properties of open sets in topology, whatever. Here we call, because we observe that all power functions have this property where that is n is an even integer, they satisfy this property f of negative x equals f of x whenever this n is an even number. Can easily verify that. And later we can generalize this notion. We call all functions satisfying this property even functions. So that's how even functions got this name. Finally, the last, second last principle of humanity. This, nobody likes to listen to something pedestrian, like we have enough routines to go through in our lives. We sometimes just want to hear something different, something that is not ordinary or something funny, right? I like to listen to jokes. So this approach works very well. I have more evidence. So these are my evaluations from my students until they're not just positive, really overwhelmingly positive, right? I'm really proud of my students, and that at least that serves as an evidence that goes to show that these principles at least worked for me. And to give end with something more lighthearted, these jokes. Well, for example, you can ask your student, why did you eat your math homework? Because your teacher said math is a piece of cake, right? And let me ask you, I like trees. I'm a mathematician. Do you know what my favorite tree is? Not palm trees. It's called geometry. Without geometry, life is pointless, right? That's why I like geometry. And why do I like to go to the forest? Because in the forest, there are a lot of natural logs. So I call the natural logs the forest function. Phoenix function refers to e to the x, right? No matter how many times you differentiate that, it doesn't change. Very tenacious. So it's like a phoenix rising from its ashes, right? It just doesn't change. So I hope everybody's just like the phoenix function e to the x, never give up. No matter how daunting the odds, never give up. You'll succeed, just like e to the x. Also another joke, pretty funny. If you're feeling cold, you can stand in the corner. Why? Because it's 90 degrees there, right? So never argue with a 90-degree angle. It's always right. And you can argue with me. I'm not a 90-degree angle. I'm an angle less than 90 degrees, meaning I'm adorable, right? Acute angle. Acute angle, you get it. Also, another funny joke. Why do I dress? Well, when my students ask me, are you going to dress up on Halloween? I usually say, well, I don't dress up because I'm a calculus TA. My job title is spooky enough to dress up. Pretty funny. So in conclusion, I think we're out of time. In conclusion, we have the 7 principles of teaching. And so I've listed them here, prepared something to read. Higher mathematics still lives too close to DOS. What I am proposing, also we highlight these 3 principles correspond to the 3 acts I showed you. Familiar, first of all, clear trails. Second of all, familiar anchors. Third, compass and drive simulation. And what I am proposing by these 3 acts is a GUI, graphical user interface for mathematics, not a weaker mathematics, but a visible one. And once math becomes visible, it becomes easier, not only for people to learn, but also for AI to read, verify, and create. Because what feeds AI is usually the defective root units, if you will, like the descriptive words from the textbook. What if you replace everything with irreducible root units? Then AI can do much more powerful things, I believe deeply. I believe that's true very deeply. And let's go back to the very beginning. I started this talk with a question: why is math so often hard? I hope you agree that I've proven this claim. And that's my proof. And it's your job to grade my proof. One last principle. I started this talk with a question. So my last principle is the principle of invitation. Begin with a question before showing your students a roadmap. Give them a reason to travel. So that's it. Thank you.
Questions?
Hope you enjoyed this talk.
How long have you been TAing in math?
Good question. For like 5 years. 5 years. It's a pretty long time. Right, any comments?
I've TA in OChem, and yeah, how do you let's say you tell a joke and then you're like how do you move into the content after you're just like, okay, anyway, let's get into it.
It's very important.
The timing, I
Yeah,
feel like it's
transition is
yeah.
important, right? You agree? I did. Well, because again, we're like humanity is very important. Students like to listen to jokes, right? We're, not something very rigorous. Of course, a professional organization, so course material is important, but we're not, the military of Southern California, Department of Defense. We're the University of Southern California Department of Mathematics, right? So, yeah, jokes work very well, and also just make sure to go back no matter how far we go, right? Go back to the course material.
Yeah.
And or just tell jokes related to the course material, playing a magic trick like this. For example, when I said something, I didn't just pull this out of the hat or in the thin air. For example, I didn't just make this equation disappear like that, right? Or make it appear again. I found my intuition, mathematical compass, instead of doing something like that, right?
Thanks.
Finally, I have prepared any other questions. Just one last slide. I call it coda. Any other questions? Yeah, let me show that to you. And not every idea is fully understood the first time it is heard. Sometimes it begins simply as a feeling that there is something there. I hope this work has given at least that feeling today. I believe there is real potential here, not only this framework, but the possibility of a different future for math writing, teaching, and understanding. This framework can be sharpened, extended, and carried much further than I alone can carry it. And I can't wait to see what you may build on top of it. If it helps open a slightly clearer future for mathematics, and if my attempt inspires even one person in the room to build boldly and leave their own mark on math and math education, then this talk will have served its purpose. So that's my claim. And I'm always open to comments and feedback, because you guys are most experts in education, and it'd be great to hear from you to further sharpen my framework and to make it serve our students better. So that's all. Thank you all very much.
Thank you.
It's